In this section, we'll focus on getting real performance out of TPUs. You'll see how batch size, numerical precision, and XLA optimized input pipelines work together, and how to scale across TPU cores without wasting hardware or breaking training stability. TPUs are built around a very specific performance mindset. You feed them workloads that are massively parallel and mostly dense linear algebra. Before execution, XLA compiles your computation graph into a highly optimized program targeting the systolic array. That compilation step trades flexibility for speed. It prefers static shapes and predictable control flow. With TPUs, you're optimizing for sustained throughput across many steps, not minimal latency for a single, highly dynamic operation. One of the most powerful tuning levers across GPUs, TPUs, and Ascend is global batch size. Global batch is simply per device batch multiplied by the number of devices or replicas. Increase global batch until you hit memory limits. If you run out of device memory before your desired batch, use gradient accumulation to simulate a larger effective batch. As you grow batch size, scale the learning rate roughly proportionally so training dynamics stay stable. BF16 is a practical compromise between speed and stability. It keeps the same 8-bit exponent as FP32, so the numeric range and training stability are similar, but it shortens the mantissa, which makes computations cheaper and faster. In practice, you run most of the heavy math in BF16, activations, weights, and matrix multiplications. You keep FP32 only where precision really matters, like the loss, master weights, and critical reductions. That mix often delivers roughly double the throughput with minimal accuracy loss. A TPU is only fast if it never waits for data. You want the CPU to read and pre-process each batch quickly enough that, by the time the TPU finishes a step, the next batch is already prepared. With tf.data, you push work to the CPU, read from TFRecords in large chunks, map pre-processing in parallel, and prefetch so batches sit ready in memory. Done well, CPU loading and TPU compute overlap, turning input latency into almost zero idle time. Data parallelism keeps one copy of the model on each device, but splits the global batch across them. Each core processes its shard, computes local gradients, then all gradients are synchronized and averaged. Conceptually, many physical TPU cores behave like one big logical accelerator. TPU strategy handles sharding, gradient aggregation, and communication patterns for you, so your code mostly looks like single-device training, just with a much larger effective batch size and higher throughput. When you move from a single device to a TPU pod, your mental model stays almost the same. You still define a model and an optimizer. You just embed that logic in a distribution strategy. The strategy object understands the TPU topology and turns your single model view into many synchronized replicas. Initialization connects to the TPU cluster, the scope ensures variables are placed correctly, and the distributed dataset API shards inputs so each core gets its slice, keeping the programming experience relatively familiar. XLA loves predictability. When your tensors always have the same shapes, XLA can compile an optimized program once and then run it extremely fast. Dynamic shapes break that assumption. If sequence lengths or batch sizes keep changing, XLA may need to recompile, adding big overhead and killing your TPU speedups. For TPU workloads, try to pad sequences to a fixed maximum length or bucket examples by length, and favor vectorized tensor ops instead of Python loops. When TPUs feel slow, it's usually because of one of four issues. First, I/O starvation. The TPU waits while you drip data from thousands of tiny files. Fix this with sharded TFRecords and prefetching. Second, control flow written as plain Python loops or if statements. Move that logic into vectorized, XLA-friendly ops. Third, host device friction. Too many transfers or callbacks each step. Keep data and computation on the TPU. Finally, XLA fallbacks to CPU from unsupported ops, which you avoid by rewriting or replacing those layers. Reading a TPU profiler starts with one question. Are we compute-bound or input-bound? If step time is dominated by TPU compute, the model itself is the limiter and you'll focus on kernels, XLA, and math optimizations. If large chunks are host to device or in feed, the TPU is waiting for data. In that case, tune the input pipeline. Better pre-processing, caching, or larger batches. Always change one thing at a time and compare traces so you can clearly see which tweak actually helped. Tuning TPUs is an iterative loop. Begin by getting a clean baseline. Run on a single core, use BF16 mixed precision, and a solid tf.data input pipeline. Next, maximize the batch size until you're close to the HBM memory limit. That's where TPUs are happiest. Then profile. Look for dynamic shapes, Python control flow, or slow input I/O and remove them. Finally, once a single core is efficient, scale out with TPU strategies across multiple cores or a full pod and repeat the process. Optimizing for GPUs usually means thinking in terms of eager execution, flexible shapes, and Python control flow. You iterate quickly, then squeeze performance with kernels, mixed precision, and good input pipelines. On TPUs, the focus shifts to optimizing the graph. You commit to mostly static shapes, large global batches, and XLA-friendly code. Conditionals and loops must be expressed as tensor operations. The trade-off is less flexibility, but higher, more predictable throughput when the graph compiles cleanly. You can think of this as a decision tree. If your model has highly dynamic shapes, lots of custom ops, or complicated control flow, GPUs are usually the better fit. CUDA, PyTorch, and TensorFlow are more forgiving and great for rapid prototyping or experimental research. When your workload shifts to massive, fairly stable transformer models and huge batch sizes, TPUs start to shine. They reward cleaner, more static graphs and are ideal for long-running, cost-sensitive production training on Google Cloud. To get peak TPU performance, think in terms of keeping the systolic array constantly busy. Push batch size up to safe memory limits. Use BF16 to boost throughput without sacrificing stability. Make sure your input pipeline prefetches so data always arrives on time. And favor static shapes to unlock aggressive XLA optimization.